heard the term calculus? No? Okay. Yes, Nihar. So, what have you heard about calculus?
Sir, I only know that Isaac Newton, he theorized it.
Yeah, Newton was one of the inventors of calculus, you can say, yes. Okay. So, I mean, most of the work in calculus, the early part of the derivations, etc., in calculus were done by one Isaac Newton, of course, and another French scientist called Leibniz. Okay. And initially, Newton and Leibniz corresponded and collaborated in their work, but eventually they had some falling out also. So there was some contradiction and also some controversy between them about who is the rightful inventor of calculus, etc. But today, both Newton and Leibniz are attributed with the early derivation and invention of calculus. Okay. So what is the subject of calculus basically about? So there are two parts of it actually. The first part of calculus is called differential calculus. So differential calculus is basically to do with the mathematics of something called rate of change. It is all about calculation of rate of change. And there's a second part of calculus called integral calculus. So we'll come to that later. We'll start with the first part, which is differential calculus, which is to do with rate of change. Now, have you heard the term rate of change? How we use rate of change in physics? Can you give any examples?
The rate of change in terms of time.
Yes, very good. That's correct. So can you give an example of the rate of change of some quantity with respect to time, which becomes important? Yes. Or any definition in physics which is to do with rate of change of time, rate of change with respect to
momentum.
Yes, very good. So what about momentum? Rate of change of momentum is what? Okay, one of the most famous laws in physics you must have heard. Newton's second law, right? That the net force acting on a body equals to the rate of change of its momentum. So if we write momentum using the symbol P, which is mass into velocity, so we know that the net force will become the rate of change of momentum. So here, this is change in momentum. And this is change in time. So that's one approximate way of defining Newton's second law using an equation that the net force acting on a body equals to the rate of change of its momentum. Any other definition where you have learned about rate of change of any quantity? What about the definition of acceleration or the definition of speed itself? What is speed?
Distance into time.
Distance divided by time, no?
Yes.
Okay. Yeah, Piyu, to answer your question, this chapter is there in the first module of physics. It is after vectors, right? The first module of physics you would have received. Okay. It is, it has two sections actually. So it has vectors, and after the chapter of vectors, it has basic calculus. It will be around page 25 onwards. Okay. So don't worry, I will tell you what all pages to read and all those things at the end of the lecture. Let's understand the introduction to calculus first. Okay. And yeah, Neha, you can start jotting down the basic notes. Okay. You don't have to write everything in detail because I'll be sending you a copy of these whiteboard notes in PDF form after the lecture. Also, another thing, this lecture is going to be recorded and you will have access to the online streaming of the video recording of this lecture. So in case you miss out any part because of internet issues or connectivity issues, don't worry, you can always revise that part later, or in any case you can revise the entire lecture later through the recording. So yeah, so coming back to the definition of speed, how do we define speed? Speed is basically rate of distance with respect to time. So speed is defined as this rate of distance covered with respect to time. Now, from here, actually, the whole story of differentiation or differential calculus actually begins. Okay, so there are so many more examples, like acceleration is rate of change of velocity. We'll come back to those examples later. Okay, but let's right now stick to this example of speed as the rate of change of distance covered with respect to time. And from this, let's understand a couple of things. So you must have heard the term average speed. Okay, and also you must have heard the term instantaneous speed. Okay, so what is the difference between these two? Let's understand that. So how do we define average speed? So let's think practically. Okay, so if you were making, let's say, a trip to somewhere, like you went from Mumbai to Nasik, or Mumbai to Goa or something, by road in a vehicle. So how would you have measured the average speed? Can anyone tell me how do we measure average speed, or how do we define average speed?
Distance upon
Yeah, sorry, come again. Distance.
time, sir.
So what we have to do for the average speed for an entire trip, for example, we have to measure the total distance, right? And divide it by the total time.
Yes, sir.
Yes, sir.
Okay, now suppose your whole trip took you 8 hours. You started in the morning at, let's say, 7 o'clock. Okay, and you reached by, let's say, approximately 3 p.m. So it took you 8 hours. Okay. So if I ask you what was your average speed for the entire trip, you would calculate the total distance traveled, okay, between 7 a.m. and 3 p.m. and divide it by the time of 8 hours, and you'd say, okay, so many kilometers in so many hours. So divide the total number of kilometers by the total number of hours. So in kilometers per hour, you will get the average speed. But can we also define average speed for a part of the journey instead of the full journey? Does it make sense?
So could you repeat what you said?
Yeah, so can we also define average speed for a certain part of the journey? Like, let's say the whole journey was from 7 a.m. to 3 p.m. But does it make sense to ask what was the average speed from 9 to 11? Yes, it makes sense, right?
Yes, sir.
You can always calculate separately also that what was the average speed for only a certain part of the journey. No? So it's not enough to say it is total distance upon total time. No? So mainly how we define average speed, we define it as the rate of change of distance with respect to time for a certain interval of time or for a specific interval of time. So that interval can be the entire journey. Like in this case, if I'm going for a journey from 7 a.m. to 3 p.m., it can be entirely for the 8 hours, or it could be for a sub part of that. It could be from 8 to 10 in the morning, then 10 to 11, 11 to 12. We could define it that way also. So average speed is something that we define for an interval of time. Okay, it is defined for a specific time interval. So let us say that is t equal to t1 to t2. Okay, and during that time interval, the average speed we can say is distance traveled during that time interval So let's denote distance as delta S. Okay, so you must be familiar with the symbol delta, right? The symbol delta, it is generally used for change. So for example, if I say delta X, it means change in X, whatever the quantity X is. So if I say delta T, it is change in T, and typically T stands for time. Okay, so here I'll say S is the distance. Okay, so delta is the change in the distance traveled during a specific interval of time delta T. So we can say it is S2 minus S1 divided by T2 minus T1. So the word definition of average speed will be that it is the distance traveled in the time interval T equal to T1 to T2. In that specific time interval divided by that time itself. Okay, so that is how I will define average speed. Okay, so let's look at a quick example of average speed. So suppose we have a situation like this, that a car starts from rest at time t equal to, let's say, 9 a.m. Okay, then accelerates uniformly at 2 meters per second square for 10 seconds. Okay, then travels at uniform speed for the next 50 seconds. So find its average speed for the first 10 seconds of its trip, for the first 30 seconds of its trip, and for the entire trip of 60 seconds. So just try out this question. I'll just give you a couple of minutes to try this out. You can also note down the definition of average speed above and then apply that definition over here. Okay. Okay, so let's look at some of the answers that I've got. Okay. So you can see what is happening here, that when the journey starts precisely at 9 a.m., the initial speed of the car is how much? It is 0. Okay, because it says that it starts from rest. Okay, and for 10 seconds, it has a uniform acceleration of 2 meters per second square. Okay. So from t equal to 9 a.m. okay, to t equal to 9 a.m. and 10 seconds, what is happening? The distance traveled, we can use this formula half AT square. Okay. So it is half into 2 into 10 square. So it is a distance of 100 meters. So the first part, and then what is happening from for the next 50 seconds, that is from t equal to 9 a.m. and 10 seconds to t equal to 9 a.m. and 1 minute. Okay. So for that much time, what is happening is this: the speed is constant. Okay. So what will that constant speed be? That constant speed will be the speed at the end of this acceleration period. Okay, so at the end of the acceleration period, we also have the formula that v is equal to u plus at. So the speed will be equal to 2 into 10 or 20 meters per second at t equal to 9 a.m. and 10 seconds. Okay. So during this period from 10 seconds to 9 a.m. and 1 minute, it will be going at a constant speed of how much? Of 20 meters per second, this same value. Okay, so for the next 50 seconds, the distance traveled will be equal to speed into time. That is 1000 meters. Okay, so once we have all this information, we can also organize this information better, okay, and answer the question that we have. So the average speed for the first 10 seconds, that is equal to what? The distance from 9 o'clock to 9 o'clock and 10 seconds divided by that time. It's 10 seconds. So that distance above you can see is 100 meters divided by the time of 10 seconds. So it is 10 meters per second. So this is our average speed for the first 10 seconds. Of the motion, right? Okay, so understood now there's a difference between the speed at the end of 10 seconds, which is 20 meters per second, versus the average speed. Right now, similarly, can you work out the second part? Try out the second part similarly. Yeah, very good. Let's work it out. So for the first 30 seconds of the trip, what we have to do is, now when we are calculating distance traveled in the first 30 seconds, so when we are calculating average speed for the first 30 seconds of motion, so we can say it is from 9 o'clock to 9 o'clock in 30 seconds. Okay. So again, the average speed is equal to distance for this time interval divided by the time interval. So what about the distance? It will be equal to the distance traveled from 0 to 10 seconds plus the distance traveled from 10 to 30 seconds. Okay. Why I have written this separately? Because during this time, it is having accelerated motion. And during this time, it is having uniform motion. So for the accelerated motion, we have already seen that the distance is this much, where A1 was 2 meters per second square. But during this time, the distance will be the uniform speed into the time of 20 seconds. Okay. Where that uniform speed is how much? It is 20 meters per second. We saw that already. Okay. So this is 100 meters plus 20 into 20. So that's 400 meters. So the total distance it has traveled between this interval to this interval. This total distance is equal to how much now? It's 500 meters. So you can see that the average speed will become 500 meters divided by 30 seconds. That is so much.
Sir, can you explain the distance part again?
So 30 seconds we are saying. Now that 30-second interval, you have to break it into 10 plus 20. Why? Because the quality of motion is changing. In the first 10 seconds, you are having accelerated motion. Okay, and from then onwards, you are having motion at uniform speed. So how you will calculate the total distance traveled in 30 seconds? Calculate the distance separately for the first 10 seconds, which is coming from this formula, half AT square, accelerated motion. And then calculate the distance traveled in the next 20 seconds. So in the next 20 seconds is going at constant speed of 20 meters per second for 20 seconds. So what's the total distance? 20 into 20, 400. Is it clear now?
Yes, sir. Yes, sir. Got it.
So for that specific time interval from 9 to 9 and 30 seconds, 9 hours and 30 seconds, the total distance traveled is 500 meters and the time interval is 30 seconds. So divide the two and you're getting the average speed.
Sir, from
Yes.
the time 10 seconds to 30 seconds, how did you find the distance?
Speed into time. So we had seen earlier that at the end of 10 seconds, what was the speed that the car reached? It reached a speed of u plus 80, that is u was 0, a was 2 meters per second square into a time of 10 seconds. So it reached a speed of 20 meters per second.
Yes, sir.
So from then what's happening? From 10 seconds till the next 50 seconds, it's maintaining that constant speed of 20 meters per second, right?
Yes, sir.
So basically we are just using our previous knowledge of the three equations of motion for uniform acceleration. Okay. We have not used the third one yet, but we are using these equations. S is equal to ut plus half at square. B is equal to u plus at, right? And you also know the third one, that v square is equal to u square plus 2as. But these equations are valid in which condition? When acceleration is uniform, right? It is for uniformly accelerated motion. Okay, so now let's come to the third part. So what is the average speed for the entire trip? So the entire trip is the first 10 seconds where it's accelerated plus the next 50 seconds where there is uniform motion. So average speed for the entire trip that is a 60 seconds of motion. Okay, let's say this. So this is the total distance. So that will be the distance traveled from 0 to 10 seconds plus the distance traveled now for the next 50 seconds. So 10 to 60. So this will now become half at square plus that uniform velocity into 50 seconds. So same way, this is 100 plus, now this uniform velocity is 20. This was 2 meters per second square. Okay. So this becomes how much? 1000. So the total distance traveled is 1100 meters, but in a time of how much? 60 seconds. So average speed is equal to 1100 meters divided by 60 seconds. So you can write that as 55 by 3. Okay. So about this much.
Sir,
Yes,
I just wanted to ask, is the sign of delta a triangular symbol?
it's like a triangle. So this symbol, this is delta, which stands for change.
Okay, sir.
All right, so this was the calculation or an example of calculation of average speed, where, just to repeat what we've learned about average speed, it is the total distance traveled in a certain interval of time divided by the time interval. So just to repeat that point, we saw that we define average speed as the distance traveled in a certain time interval divided by the time interval itself, right? So we can write it mathematically as the distance traveled in a time divided by that particular time interval. Now, as opposed to average speed, we also have a second term that we define called instantaneous speed. You would have heard this term instantaneous. What do we mean by the term instantaneous speed? Can anyone tell me?
Sir, the speed of an object or a body at any instant.
Okay, so it's the word definition is that it is the speed at an instant or like at a moment of time. So how do we actually measure instantaneous speed? Can you think of any instrument that is used to measure instantaneous speed? In practical everyday life, what measures instantaneous speed? Come on, all of you know the answer to this, right? What is the instrument?
Sir, it's normally on the car, but I forgot the name.
It is called a speedometer, right?
Yes, sir. Yes.
So
Sir.
for example, the reading of a speedometer in a vehicle. Another example is, I'm sure all of you watch some sports. So you know that there is something called a speed gun. Used to track the speed of moving objects. Okay. Like you have speed guns in baseball or speed guns in cricket to measure the speed at which a bowler is bowling. Okay. Or you have a speed gun in tennis to measure the speed at which a player is serving the tennis ball, etc. So what these things do, how do they measure the speed at an instant? So for example, what does the speedometer do? When you are typically traveling in a vehicle, you will see that reading of the speedometer, that doesn't remain constant, right? It changes from moment to moment. So because typically you are either accelerating or decelerating. Very rarely you are moving at a uniform speed for any particular interval of time. So how the speedometer actually measures the speed at a particular instant? Any idea how it does that?
The RPM.
Yes, very good. So the speedometer, what it does is it measures RPM. That is the rounds per minute. So it measures the rate of rotation of the wheel. It measures that in RPM, that is number of rounds per minute. But how does that convert the information of rounds per minute into speed? Can you tell me that? Any idea? Okay, so tell me something. I know the number of rounds per minute. From that, can I calculate the time taken for one rotation?
Yes.
So for example, if I know that a vehicle is making, let's say, 120 rounds per minute, I mean the wheel is making, so this is the rotation speed of the wheels. So from that, what can I tell about the time period of the wheel? What is the time period for a single rotation? 120 rounds per minute. Okay. So that means in 60 seconds, it's making 120 rounds. So in 1 second, it will make how many rounds? Two rounds. Okay. So that means how much time per round? 0.5 seconds. Correct, no?
Yes, sir.
So now once you know from RPM the time period for one rotation, how do you calculate instantaneous speed from that? Okay, so that brings a question that a rotating wheel on the ground, how much distance it travels in one rotation? Okay. A rotating wheel is typically moving like this. Okay. So let's say you have a point on the wheel, which is like this. Now, when it completes one full cycle, where it reaches again? It reaches here. So what is this distance it travels? It travels a distance 2 pi r. Does it make sense?
Yes, sir.
It travels a distance of 2 pi r, where r is the radius of the wheel. Okay. So what is the instantaneous speed or the speed in one during this small time? So how it measures the instantaneous speed? By measuring the distance with respect to time for one cycle of the wheel. So what is the difference between average speed and this particular instantaneous speed? Now compared to the journey time, one cycle of the wheel will be a very small amount of time. Like in this case itself, for 120 RPM only, it is half a second. But typically, it might be much larger the RPM. So we are talking about a much smaller interval of time. Similarly, what a speed gun does, a speed gun typically has some way of mapping the motion of an object for a very small distance using an infrared reflection technique or an infrared detection technique. So for example, if we are talking about the speed gun in a game of cricket, so as the bowler is bowling the ball, releases the ball from some point here. So it measures the distance with respect to time for a very short interval of time. So what the speed gun does is it has infrared sensors. So during a very small part of the motion from here to here, it measures the time taken and the distance traveled, and it accordingly measures the distance divided by time. And from that, it measures the release speed of the ball. So basically what an instrument does when it's measuring instantaneous speed. Okay. So what do we exactly mean speed at an instant? We mean rate of covering distance with respect to time, not for a time interval from T1 to T2, but at a particular instant. That means for a very short amount of time during that instant. Okay. So instantaneous speed means rate of distance with respect to time for an extremely short interval of time. So what do we mean by extremely short? So at the level of measurement, it means that it is the shortest that is possible for an instrument. Okay, so the more complex our instrument is, or you can say the better reading our instrument is giving, the shorter interval of time it will be. So for example, if we are using some analog technique, okay, like the speedometer, okay, and it's measuring the distance traveled with respect to time per millisecond, then it has a certain level of accuracy. But if we bring in some digital instrument like an infrared sensor speed gun, and it is able to measure the speed with instantaneous speed in terms of distance by time for a microsecond, then obviously the second instrument is much better than the first instrument, because it is giving us for an interval of time which is 1 micro, that is 1 millionth of a second, whereas the first instrument which was giving us per millisecond, so that was 1,000th of a second. So obviously the second one is that much more accurate, because that is giving us in 1 millionth of a second. The first one is giving us in 1,000th of a second. So by extremely short interval of time, we mean that according to our, let's say in terms of measurement, the shorter the interval of time, the better the accuracy of our measurement, right? So if something is extremely short, then it is extremely accurate in measuring the instantaneous speed. Is this point clear to all of you?
Yes, sir.
Okay. So now let us interpret this in a slightly different way. Okay. Let's think of this in terms of the graphical interpretation or the graph. Okay. So average speed versus instantaneous speed in a distance time graph. Okay. So now let's say we are talking about some more practical type of everyday life problems. So the distance time graph is not something which is, very uniform or anything, but it's a bit more random. So our distance s, let's say in meters, and t time in seconds, so this graph, let's say for a practical motion, okay, which is not very uniform, it is looking something like this. This is how it will typically look for an actual everyday life kind of motion. It will not be very uniform. So the distance, okay. So in this, how do we interpret the two quantities, average speed and instantaneous speed? So first, let's start with average speed from t equal to, let's say, t1 to t2, where on this time axis, t1 lies over here, t2 lies over here. So how we'll calculate the average speed using the graph? Okay. So suppose we've actually done an experiment, and during that experiment, we have measured the distance traveled at various different times. Okay. We plotted those on some graph paper, and we've joined that with a smooth curve. So we've come up with some distance versus time graph like this. So now using that distance versus time graph, I want to find out that during this time interval t1 to t2, what was my average speed? Okay. So what I'll have to do is I'll have to plot this point on the graph at time t1 and see that from the beginning of my journey, what was the distance traveled at that point of time? It was, let's say, s1. Then again, I'll have to plot this other time t2 as a point on the graph which has the time coordinate or the value of time as t2. So correspondingly, I can measure that the total distance from the beginning at that point of time was s2. Okay. So a little while back, okay, Sakshi, you asked the question why we use delta S in the formula for average speed. Now it will become clear to you. So see, S1 is basically what? S1 is the distance traveled from the beginning till the time t1. The beginning, that being t equal to 0. What is S2? It is the distance traveled from the beginning to the time t2. But now, according to average speed, what I want to calculate? I want to calculate the distance traveled during this time interval. No? So it is distance for time t equal to t1 to t2 divided by the time interval. Okay. So what is this distance going to be? It is going to be delta S, that is the change in distance from t1 to t2. So that's why it's going to be S2 minus S1. So this difference of S2 minus S1, that is only what we call as the change in distance. So from the beginning, the distance was S1 at T1 and it was S2 at T2. So what is the distance traveled from T1 to T2? It is the change in the quantity S from T1 to T2. So it is S2 minus S1. Similarly, what is the change in time during this time? It is nothing but T2 minus T1. Understood the points actually now? Why we use delta S for distance in average speed?
Yes, sir.
Okay. So you can see in the graph over here that if I just extend this line, okay, then this quantity over here is actually my delta T. It is the time interval T2 minus T1. And this quantity is nothing but my distance traveled during that time interval. It is delta S, which is S2 minus S1. So this is how I calculate it from the graph. Okay, this is my average speed. During that time interval. Okay. So just make a quick note of this graph. So first we are looking at average speed in terms of the distance time graph. Next we will look at instantaneous speed and what is the difference between the two. Okay. Now in the same graph, let's try to understand what we would mean by instantaneous speed at a particular moment. Okay, so suppose I'm looking at the information about that particular experiment, okay, where I measured distance versus time and plotted it into a graph for a certain journey. But later I'm using that graph to measure instantaneous speed and not average speed. Okay. So how I would do that from the graph? Let's try and understand that. So in the same graph now, suppose I want to find out instantaneous speed at a particular point of time. So let's say at this time, t equal to t naught. I want to find instantaneous speed v at the instant t equal to t naught. How I would do that? So what I'd have to do is I'd have to, of course, plot that point on the graph where the distance it has traveled from the beginning till that time t naught is, let's say, s naught. Okay. But then instead of taking an interval of time from here to somewhere larger, I have to take a very, very short interval of time. So what I'll have to do is I'll have to zoom into this graph. Because imagine, compared to the journey time of a car, what is the time taken for the rotation of one wheel? It's a very, very short interval of time. So I'll have to zoom into this and take a very close point to this, such that from this point to this point, when I track the time traveled, it is negligible and the difference in time is very short. So this part is my change in time, but my change in time is extremely short. Like a millisecond or a microsecond, whichever is feasible according to my measurement. So accordingly, between this point and this point, the distance traveled will also be very short compared to the total distance. So this is the distance traveled during that very short interval of time. So when I zoom out of this graph, it looks like the 2 points that I've drawn are almost the same. In fact, the shorter the value of time I've taken over here, the closer these 2 points will be. So this will be equal to distance. So this calculation will come down to distance divided by time, but with the condition that for an extremely short interval of time. So I cannot replace delta t with t2 minus t1 and delta s as s2 minus s1, because it is not like two distinct intervals or points of time like t1 and t2 over here. It is like this time t naught and something very, very close to it. Okay, so this second time over here is t naught plus delta t, where delta t is very, very small. Okay, so you can see that when we look at technically what is the meaning of instantaneous speed, it is a much more complex thing compared to average speed. That's why its measurement is also that much more complex. So for example, in the analog method, we need a speedometer which is able to measure the rate of rotation of the wheel, and from that back calculate that during one cycle of the wheel, how much distance it's traveling. Or we need a speed gun which has an infrared sensor, so it is able to map the motion of a moving object for a very, very short interval of time. Whereas calculating average speed is not at all that difficult. You just need to keep track of what the total time of your journey is, and by some method you should be able to measure the path length, that is the total distance. Okay. So it is this complexity of calculation of instantaneous rate of change. In this case, instantaneous rate of change of distance with respect to time. This complexity itself resulted in the invention of calculus. In fact, more specifically, the invention of the first part of calculus, which is differential calculus. Okay, so to understand this whole problem a little bit better, the difference between instantaneous speed and average speed, let us go back to Newton's time. Okay, sometime around the late 1600s, when he invented the concept of gravity, or you can actually say he discovered gravity. So let's think about his line of thinking during that point of time. So all of you would have heard about that famous story that, that legendary story that he was just sitting in his garden and he observed an apple falling from a tree, and by just thinking about the motion of the apple, how it is falling towards the ground with increasing speed, he realized that the ground is pulling it, or the earth is pulling that apple towards it, and from that he coined the term gravity and discovered the concept of gravity. Okay, so of course that is the legend, whereas actually it was not like he realized about gravity in just a moment. There was a lot of thought process which had gone into that for years before he realized the result of that particular observation, that a falling object has increasing speed, so it is being pulled by some kind of force. But the observation of that same thing, an object moving with acceleration, also resulted in the beginning of the study of calculus actually, or the beginning of the study of rate of change. So let us understand rate of change in terms of average speed and instantaneous speed, in terms of the basics of Newton's laws and how it is connected. Let's see. Okay, so as you know, Newton's first law, what it says that until and unless some force acts on a body, it has a tendency to continue in its state of uniform motion. So basically, one way of interpreting first law is that if the net force on a body is zero, then it will continue in its state of uniform motion. Okay, so net force on what? So if the net force on a moving body or particle, if that is zero, then it will have a tendency to continue in uniform motion. So what we mean by the term uniform motion? At the most basic level, by uniform motion, we mean that it covers equal distances in equal time, in equal intervals of time. Okay. So let's visualize this at an experimental level. So how we could visualize this is, imagine a body that is moving under the condition that the net force on it is zero. So a typical condition like that would be if we somehow manage to create a surface which is perfectly smooth, so there's no friction. So we have a frictionless surface, or what we call in physics a perfectly smooth surface. Okay. Now on this surface, if there is a block or some object like that, which we've initially given a push, so it's moving at a uniform speed, okay, v naught, but there's no force acting on it, so its acceleration is zero. So what we'll observe, that suppose it was here at time t, after some time it is over here, so it has covered. So now suppose it is here at t plus 2 delta t. So that means that whatever distance it would have traveled from here to here, let's say that was delta s, that should be equal to the distance it's traveled from here to here, because it's an equal interval of time. From here to here, the time is delta t. From here to here, the time is again delta t. So in equal intervals of time, it is traveling equal amount of distance. So what this would mean in terms of a speed versus time graph, sorry, in terms of a distance versus time graph, let's try to visualize that thing next. Okay. So if you're looking at a distance versus time graph for this particular motion, what kind of graph we would expect? If something is traveling equal intervals of distance in equal intervals of time, what do we expect about the graph of the distance versus time?
Straight line.
A straight line.
Uniform.
That's good. We observe that it will be a straight line, because a straight line has that property that it has uniform rate of change. So now for such a graph, if I say what is the instantaneous speed, what will the answer to that be? So for example, if this speed was suppose 20 meters per second, so what we'll observe that in the first second, how much distance it would have traveled? 20 meters. But same distance in the second also. So at t equal to 2 seconds, it would have come up to 40 meters. At t equal to 3 seconds, it would have come up to 60 meters, and so on and so forth. So for such a graph, we can say something very interesting, that whether we are looking at instantaneous speed or we are looking at average speed, they would both be the same. Isn't it the case? For this type of a graph, okay, and that would be nothing but the slope of the line. So the slope of this line is nothing but delta s by delta t, which would be our 20 meters per second or our uniform speed p naught. Okay. So because it's a uniform speed, so what we'd observe over here, that in uniform motion, okay, the instantaneous speed at any point of time remains constant. That's the first thing that we observe. And this, so v at any instant is equal to this v naught in this particular case. Okay. And the instantaneous speed equals to the average speed. Okay. So that you can easily understand by observing this graph, that if I take any 2 points of time and calculate S2 minus S1 upon T2 minus T1, that will be the same as the calculation of delta S by delta T for a very short interval of time delta T. Okay. So that is how the relationship between instantaneous and average speed is working out in this simple case when the motion is uniform, because the net force on an object is 0. Okay. Now note this down, and next we will see the case of an accelerated object like the apple falling towards the ground, which Newton was observing, and how that is different to this. And by observing the difference between that one and this one only, he started thinking about the concept of instantaneous rate of change, how it can be different from average rate of change. And from there, the whole mathematics of differential calculus developed. The science of instantaneous rate of change, it developed from that point of time. So anyway, write down this one first. Okay, jot down a few points about this. Then we will come to the second case I was talking to you about.
Amen. Yeah.
Sakshi Shah, you're requested to mute your mic.
Okay, so hope this example is clear.
Just a minute, sir.
Okay. So Manav, to explain the answer to your question that why the instantaneous speed equals the average speed. Okay, let's look at the graph in little bit more detail. So in this case only, if our graph of distance versus time is a straight line, okay, which is like this now. So this straight line has to be drawn such that the rate of change of distance with respect to time, which is the speed, is constant at 20 meters per second. Okay. Now in this, if I measure the instantaneous speed, sorry, the average speed for some time t1 to t2, what will that be equal to? That will be equal to the slope of this straight line only. That is the concept of straight line. That tan theta equals to y2 minus y1, in this case s2 minus s1, divided by x2 minus x1, which in this case is t2 minus t1. Okay, so that will not be equal to this constant, tan theta. So you can see that average speed for a time interval, which is s2 minus s1 divided by t2 minus t1, which is tan theta, is uniform because it's a straight line graph. So whether I select these 2 points or any other points randomly, they will give me the same value of tan theta, because it's a straight line. So it has the same theta between any 2 points. Which is uniform. So this point is clear, Manav?
Yes, yes.
Okay. Now in the same thing, if I want to measure the instantaneous speed at some particular time, so what I'll have to do is, let's say I want to measure the instantaneous speed at this time. So I will draw this point over here, and then I'll draw another point very close to it, and I'll measure that delta s by delta t for those 2 very close points. But again, when I zoom into that, it's the same triangle. It'll have the same theta, it'll have the same slope. So instantaneous speed, which is equal to delta s by delta t, for the condition that delta t should be very small. It should be an extremely small interval of time. But even that will give me the same, na? That will be tan theta, which is uniform. So that is the property that a straight line has. Okay. That the slope between two distinct points like T1 and T2 and the slope between 2 points which are very close to each other, like this T and T plus delta T, they are the same, and that is equal to tan theta. So that is why the instantaneous speed at any point of time equals to the average speed for the entire journey, equals to that constant quantity, which is the slope of the straight line.
Yes, sir, got it.
Got it? So that is what you can observe now about such a motion that is happening, that as long as we are not applying any force on that moving body, it will have this kind of motion, that it covers equal distances in equal intervals of time. So if we just calculate that distance divided by time, it will also give us the instantaneous speed at any point of time. Not just the average speed for the journey, but it will also give us the instantaneous speed at any point of time. Okay. Now, if you observe the difference between this and the case of the falling apple, okay, that Newton had observed, you'll see there's a huge difference. Okay, in the case of a falling apple, so the next we look at an accelerated body. So we come to application of Newton's second law, that there must be some net force acting on it, which is equal to the rate of change of momentum, which will become equal to mass into acceleration if the mass of the body is constant. Okay, so let's take the example of a body in free fall or an object in free fall under gravity. So you can say under the action of the Earth's gravitational pull. Okay, so what would we expect to observe about the distance versus time in such a graph, in such a case? It would definitely not cover equal intervals in equal intervals of time. Na? It would not cover equal distances in equal intervals of time. Why? Because the motion is accelerated. So what we would observe about the graph of such a motion is that it would be like this. It would be curving like this. How I know it would be curving like this? Because if I take equal intervals of time, the amount of distances traveled would be increasing. So here, if I've taken this as delta t, 2 delta t, 3 delta t, 4 delta t, like this. But in this, you can see that distances traveled are different. So you can see these are increasing. These parts are increasing while the horizontal intervals are remaining the same. So it is traveling unequal distances in equal intervals of time. In fact, progressively these distances are increasing in equal intervals of time. So for such a graph, what is the difference between average speed versus instantaneous speed? So let's understand that. Okay. Just a moment, I'll be right back. Okay, so now this graph I hope is making sense to all of you, how it is different from the case of uniform motion, because it has to curve like this, because force is acting on the body, it's accelerating. That means as you're progressively increasing the time, it's covering more and more distances in the same intervals of time. So that is the approximate meaning of accelerated motion. Okay. Now in context of this, let's think of what is instantaneous speed versus average speed in a more technical manner. Okay. So for such a graph, what is average speed? Let's come back to that. So from the definition of average speed, what is it? It is the total distance traveled in a certain time interval. So if that time interval is T1 to T2, is the total distance traveled during that time interval, that is S2 minus S1 divided by the time interval. So in the graph, let's see what that looks like. So if I have this type of a graph, so this is, as you can see, distance time graph for a non-uniform motion. So in this case, it's an accelerated motion. It's not a decelerated motion, it's an accelerated, because you can see that the speed is increasing with time. Okay. So in this, what is the average speed in a certain interval from T1 to T2? How we would measure it? So it would be equal to S2 minus S1 upon T2 minus T1. So once again, repeating what we've done earlier, suppose this is the time T1 and this is the time T2. So what we have to do is we have to plot this point here, where this is my S1, and we have to plot this point here, where this is my S2. But the interesting thing is now this calculation, that is S2 minus S1 and T2 minus T1, this has a special significance in terms of these 2 points. This is nothing but S2 minus S1, and this is nothing but T2 minus T1. So the ratio of these 2 things is nothing but the slope of something. But slope of what? A slope of a line if I join these 2 points with a straight line. So supposing I do that operation, that I just join these 2 with a straight line, then average speed between this point and this point also becomes the slope of this straight line. So that becomes another way of defining average speed for us now. It becomes a graph way of defining that the average speed between 2 times T1 and T2 is nothing but the slope of a straight line joining those 2 points. So such a straight line is given a specific name. It is given the name of, might not have heard this name before, but it is called a secant line. Okay. Whereas this was the graph of S versus time graph. So the average speed between 2 times T1 and T2, or for an interval of time T1 and T2, that also becomes equal to, as you can see, if this angle is theta, it becomes equal to tan theta. In other words, it becomes what we call the slope of the secant line joining the 2 points at t equal to T1 and t equal to T2 on the S versus T graph. So in this case, I will call it the S versus T curve, because the graph is curved. So that becomes what we call the geometrical definition. Okay, this is the geometrical definition of average speed, or the graph definition. You can say the graphical meaning of average speed. It is the slope of a particular type of line, but which type of line? It is the secant line when it's a curve. When your S versus T graph is a curve, then how we interpret in terms of graph or in terms of geometry, what is the average speed for a certain time T1 to T2? It is the slope of a line joining those 2 points of time T1 and T2 on the graph. So that kind of line is called a secant line, and we interpret the average speed as the slope of the secant line. Okay, so just make a note of this first, then we'll come to instantaneous speed, which is the more important and more interesting point for us. Okay, so don't worry about formulae and all that. We'll discuss a lot of numerical examples of this, but right now just understand this conceptually. So the moment we have a curved graph for distance versus time, the interpretation of average speed becomes a little different. Okay, so earlier when our distance versus time graph was a straight line, then average speed or instantaneous speed were one and the same thing, and that was equal to the slope. V average was equal to V, which was equal to the slope. Okay, but the moment we are having a situation where distance versus time graph is curved. Okay, now I'll take a more general case. It could be curved in such a way that it accelerates for some time and then later decelerates also. Something like this is also possible. But now when I talk about V average, It is the slope still, but the slope of what? It's not the slope of the curve, no? It's the slope of some kind of straight line. So which type of straight line will tell? If this is my T1 and this is my T2, then I have to join these 2 points with a straight line. Okay. And it will be the slope of that straight line. So this straight line is called a secant line. So it is the slope of the secant line. Okay. Joined between T1 to T2. So that is the general definition of average speed in terms of the graph interpretation. Okay. Now in this, let's talk about the instantaneous speed. For the same thing, now what will be the interpretation for instantaneous speed? So if we just go with the meaning of instantaneous speed, that it is distance traveled divided by time for a very, very short interval of time. So what we'd come up with in terms of the graph meaning, let's understand that. So let's go back to our object in free fall, like the falling apple that Newton observed. So that is having a distance versus time graph, which is curving like this. So it's an accelerated motion. Let's try and draw that more smoothly. So this is the distance versus time curve. In my particular example, it is a body in free fall, body or particle in free fall. So now I want to calculate instantaneous speed. Okay, at some instant, let's say t equal to t itself. Okay, so let's say that particular instant of time is over here. So the difference now is that I have to calculate the distance divided by time only, but for a very, very short interval of time. So if I wanted this to be very accurate, I want to make that interval of time so small that the second point almost merges with the first point. So as usual, I have to zoom into this graph as much as possible. So if I zoom into it as much as possible and draw a second point over here, which is as close as possible to the first point. The closer it is, the more accurate my reading will be. Okay. So now this is my very short interval of time from here to here. Extremely short interval of time. Okay. And correspondingly, this is my delta S. Okay. So what we'll see is something very interesting. If we are to join these 2 points, which are like consecutive points on the graph, okay, but if we are to join them with a straight line, then we will get something called a tangent line to the curve. Instead of a secant line, we'll get a type of line which is called the tangent line. And this thing that we are calculating, the instantaneous speed, it will be nothing but the slope of the tangent line. So when I zoom out of this graph, this tangent line will look like a line that is just about touching the graph at one point only, because these 2 points will appear to merge with each other. Okay. So when I zoom out of this graph, you can see that this line that I've drawn is not going through 2 distinct points, but rather it is touching the graph at one particular point and going through the next consecutive point on it. So this is called a tangent line. Okay. And just to show what we've done over here in the graph to draw this, if we were to magnify this, if you were to magnify this, then that at that particular point, let's say that it's curving like this. Okay. and we have this point which is corresponding to time t, and then this point next to it which is corresponding to time t plus delta t. So this is that very short interval of time delta t, and this is that very small amount of distance it has traveled during that short interval of time delta t. Okay. So given that when we magnify this, we are joining these two with this straight line, which is the tangent line. You will see that it is again nothing but slope of the tangent. You see that small triangle here, then this angle is again theta. So you can see that the instantaneous speed, which is delta s by delta t for this very short interval of time delta t, it is nothing but slope of the tangent line at the point t equal to t. Okay, so we'll come to a technical definition of tangent line also, but this is what it looks like on the graph. So for example, on a graph like this, you can understand why the speed is increasing with time, why the instantaneous speed is increasing with time. Because if the distance versus time graph is curving like this, now you see the tangent drawn at this particular point of time, it's like this. You see the tangent drawn after a bit of time, it's like this. So you can see it has increasing slope. So you can see that for this particular distance versus time graph, if you compare the instantaneous speed at two different times, not the average speed, but the instantaneous speed at two different times, okay, you can see
So you are not audible.
Sir, you are not audible.